So before I move on, questions so far? Do I need to go back to anything? No, I just advanced the board. Okay. All right. So, okay, we got about 15 minutes left. I'm gonna talk some briefly about the notation that we'll use in this class. Okay.
Hey, Professor,
And yes.
one quick question. Is there a way, it's not a big deal, is there a way you can scroll instead of flipping pages like blatantly every time, or is it's not that big a deal, but
So I can't do that with Zoom Whiteboard. I could look for another application that I could do that
yeah,
with.
it's
Did,
it's not a huge deal just because like I maybe miss one thing and I could go to the lecture, the
oh,
record.
okay, I'm sorry. I
No,
will
I
do
didn't
that before I advance. So,
actually, I got everything here, just like, I don't know,
okay,
in
all right,
case.
I
But thank
gotcha. Now it makes sense. Yeah. So then you kind of always have everything up above. Yeah. Would other people prefer that or how it is now? How many people would prefer?
I mean, are you
How
on
many people are
Windows?
fine with how it is now?
I'm pretty fine either way. I will say like OneNote is kind of a little bit better than Zoom Whiteboard if you're already on Windows, but if you're like on Linux or something, I don't see why you would have to really switch all the way over to something else.
Okay, yeah. I'm on a Mac. I looked at a couple other programs, but Zoom Whiteboard seems to be, yeah, maybe
Also,
the,
since it's recorded, it's not a big deal.
okay, cool. But yeah, thanks for bringing it up. I'll make sure yeah, not just advancing so quick before everybody has everything down. Okay. So notation, maybe most of you have seen this before, but we'll kind of interchangeably use these three different ways of representing derivatives, partial derivatives, and most of the derivatives that we'll be dealing with are partial derivatives. Okay. The different types of PDE that we're going to encounter, okay? One is the linear transport equation. And this is the one that I wrote down at the beginning, but oftentimes you have some speed of the transport. So this is a first order linear PDE, okay? It models really just flow kind of down a one-dimensional river, okay? You have some concentration of chemical, or you drop something in a river, and everything just gets transported along, okay? Or if you think of the logs moving in Frogger, right? Anything that you put on there is just going to get transported at a constant speed, okay? Nicest sort of, maybe simplest PDE that you can have, okay? The next one that I'll write down is what's called the heat or diffusion equation. No doubt, like an undergrad PDE course would talk about this. And this is really that you have some concentration or temperature or heat energy, and it disperses according to the divergence of the gradient. So basically everything wants to spread out. Heat wants to spread out, and it does so according to connectivity or a diffusion constant, K in this case. And then Q would be like your unknown function. So, sorry, it would be like a forcing function. So maybe some energy, heat that you're injecting into the system, or if you're thinking of like, this is some chemical concentration, this would be the source of that chemical somewhere in your domain, okay? So this is, again, second order, and linear, and we will deal a lot with this equation, okay? Next one that we'll deal with a lot is what's called the wave equation, and we talked about that in the first example that we discussed, okay? This is a second order equation, and rather than a transport equation where you just have transport in a single direction, this model really, you have transport or wave propagation in two directions. So on a one-dimensional line, you have some concentration or disturbance in some active medium, and it just propagates outward from the origin of the disturbance. In 2 dimensions, this would be, maybe like a target pattern. In 3 dimensions, it would be like a growing sphere. And so we'll talk a lot more about that when we get to the wave equation, okay? Here in this case, this delta really represents, I'm gonna say for example up here, okay? Just the sum of the second order spatial derivatives, okay? So like in 3D, okay, the diffusion operator just looks like the sum of those 3 second order partial derivatives in space, okay? The Laplace equation is the last main PDE that we'll think about, which is linear. And this says the diffusion operator acting on your unknown function u is equal to some function f that's specified by the problem, okay? And a lot of times people think of this as maybe like a steady state solution to the heat or diffusion equation. So it's often a model of what happens to like a 2-dimensional plate when you specify the heating of it on the outside. What does it settle down to over time? Okay. There's lots of other PD examples I could give. They're actually in the lecture notes online, so I won't just keep writing them down. But I did want to hit on the ones that we're going to encounter a lot of in the course. Okay. So, so let's talk some about how to work out some solutions from some of these examples, okay? And in particular, I want to talk more about examples with waves, okay? If you couldn't tell already, okay, the book and also our department has a long history of nonlinear waves, and so this course will build around a lot of examples of wave propagation in PDEs. I think this is one of the interesting solutions to PDEs that has a lot of applications, and people know a lot of ways for analyzing these solutions and obtaining these solutions. It's not the only set of examples we'll go on in this class, but we will be talking a lot about waves. So so again, let's return back to the linear transport equation. Okay, so the linear transport equation says that I have an unknown function u, okay, and essentially it's temporal derivative plus some constant c times the spatial derivative is equal to 0, okay? And so this, I'm just going to tell you what the solution is. I'm not going to explain how to get this solution. We'll get to that later, okay? Is f of x minus ct. Probably not a big stretch of the imagination if ut plus ux equals 0 had the solution f of x minus t, that the solution of this PDE would be f of x minus ct, okay? So this is similar to the warm-up problem, okay? But now we want to add in an initial condition, okay, which is u of x0 is equal to u0 of x, okay? So in this case, how do we make sure that we pick a function f that is compliant with this initial condition? Okay. Well, what we can note is that if I take this solution and I say, well, u of x0, what is it equal to? It's equal to f of x. Okay. I now have this additional initial condition that tells me that that should be equal to u0 of x, okay? So just like in ODEs, the way that I specify my constants in ODEs is to apply my initial or boundary conditions. In this case, in PDEs, the way if I have a whole family of solutions, the way I pin down what function in that family I should use is using the initial condition in this case. And so this implies then that u of xt is equal to, sorry. Here we go. All right. u0 of x minus ct. Okay. So that's our solution with the initial condition specifying it, okay? And we could also specify boundary conditions, okay? So far, I haven't even really told you what domain this is on, okay? But if we have a finite domain in X, okay? So let's call that, omega, and it's a subset of R, okay? Or even if it's just a subset of R, okay? Like if it was just the positive reals or something like that, we're going to come up against a boundary, and so we need to deal with that, okay? So then, in this case, we would also have boundary conditions. Okay. And I think especially in the case of the transport equation, when you're just starting to cut your teeth on these PDEs, it can help to draw a lot of pictures, okay? And so let's say this is our boundary. We'll call it Q, and this is equal to x of t, xt, where x is non-negative and t is non-negative as well, okay? So along this boundary, this is our x boundary and this is our t boundary, I have a function phi of x, okay? Along this boundary, I'm going to say I have a function psi of t, okay? So in this case, right, the solution I have, okay, in general is just given by u of xt is equal to f minus ct, okay? That's the one I wrote down before. You can check it by plugging it into the PDE, okay? But now how do I deal with these two solutions, or these two boundary conditions? One's a boundary condition, one's an initial condition. Sometimes people call initial conditions boundary conditions still. Okay, so we know how to deal with these boundary conditions. We have a clue based on what we did last time, right? We basically just plugged in, okay, the boundary into the general solution that we have and used it to construct an equation for what that unknown function f should be, okay? We just have to do that in pieces now, okay? So the issue now is that I have two pieces to my sort of boundary and initial data. I have the piece that's along X and I have the piece that's along T. And so if I specify U of X0, what I know is that this should be phi of X, okay? And if I plug in what I already have for my initial condition, that's just f of X. But this is only going to apply when X is greater than or equal to 0, okay? Along the boundary here, right, I have, so I'll write this down here, U of X of 0 equals phi of X, but U of 0t equals psi of t, and that holds for t greater than or equal to 0. So U of 0t now is psi of t, and that's f of minus ct in this case, okay? And that again applies when t is greater than or equal to 0. But how do I get this in a usable form, okay? I'm going to change variables. I'm going to write y equals minus ct. So that means that t equals minus y over c. And this formula now becomes f of y is equal to psi of minus y over c, okay? And this in particular applies for when y is less than or equal to 0, okay? So I've fully specified my unknown function f, okay? When its argument is positive, I'm going to use my x initial condition. When its argument is negative, I'm going to use my t boundary condition, okay? So what happens is the way that I specify this function is sort of to fold, follow the fold of the boundary and initial condition that meets here at the origin, okay? And so that's an idea with initial boundary value problems that, again, we'll come back to when we dig more into the transport equation, okay? So I'm up against the end of time. Are there questions about what I just talked about or anything else that we covered so far? Okay. All right. Well, that's the end of the first day. Incidentally, office hours are always after class on Monday. So we have office hours from now until 2. If you want to stick around and have questions, you're welcome. Otherwise, class dismissed.
Thanks,
So
Zach.
see you all. Yep. Thank you all.
Thanks.
See you on Wednesday, if not before.
Could you say briefly what you mean by when the argument is negative, we're going to use the y stuff? I just don't see when we would be given a negative argument, I guess.
Yeah, that's a great question. So if we have u of xt is equal to f of x minus ct, right?
Mm-hmm.
So when is this so that's our full solution, right?
Okay.
So when is x minus ct going to be less than 0? Well, whenever x is less than ct.
Right.
So if you draw x and t here, right? You can draw the line x equals ct here. Whenever x is greater than ct, the solution is specified by the initial condition that's along x. Whenever over here, x is less than ct, the solution is specified by the boundary condition here along t. So the idea is just that when you have an initial boundary value problem like this, that's in the upper right quadrant, right? your solution sort of gets split by this. This is actually a characteristic. This is just the characteristic x equals CT, okay, into just two regions, okay? So your full solution here would be x, u of xt would be equal to phi of x minus ct. Sorry to squeeze this in here. If x is greater than ct, and it's going to be psi of minus 1 over c x minus ct whenever x is less than ct.
Okay, awesome. That makes a ton of sense. I was just not seeing that picture before.
Yeah. Okay. Yeah. So I'm going to circle back to it at the beginning of next lecture before we move on to other stuff.